तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we shall continue our discussion on I squared L. We have seen that I squared L, although it has a lot of attractive features like low power dissipation, high packing density, the main drawback was speed, and there has been a lot of effort in that direction, okay, how to improve the speed of I squared L. And last class we saw how technology, okay, improvement in technology helped reduce the speed, okay, by having a different geometry where you reduce the areas where you the excess charge is stored, etc. Okay. Now, there has been another direction in which work has gone on to reduce the propagation delay or improve the speed, and that is by making certain modifications in the circuitry itself, okay, small modifications, and we shall see how that has we shall take up a few cases now. Okay. So, one of the variations, I should say, of I squared L has been the Schottky transistor logic. Okay. This is a particular logic family called Schottky transistor logic or STL. Okay. And this is a variation of the well known I squared L. Okay. The basic circuitry basic cell of this Schottky transistor logic looks like this. So, this you have diodes here, Schottky diodes, and this is the transistor. Okay, you can well recognize that this is a Schottky transistor in fact. Okay, it is a bipolar transistor with a Schottky diode between the base and collector. Okay, I have drawn it out, including instead of just drawing the symbol of a Schottky transistor, because we will require this for some calculations. Okay, here you have the input, here is the VCC, you have a resistance here. Okay. So, this is another difference from the normal I squared L, that is, instead of a PNP transistor acting as a current source, you have a resistance. Okay. So, in fact, you will require resistances in this circuit, okay, and each cell would have should have a separate resistance, because you cannot have a common resistance, okay, in which case all the input points would be basically shorted. Okay. So, that is a major difference. Here the output, okay, is taken through so this is out 1, out 2 and out 3, say the output is taken through Schottky diodes, all right. Okay. So, common collector point, and then you have Schottky diodes, because just like you have multiple collectors, okay, in a I squared L, it is a necessity. Okay. So, you have you must have multiple outputs in this case, and this is how it is taken in this particular logic, all right. So, this Schottky diode, let me call it SD1, okay, and these Schottky diodes, let me call it SD2. Okay. All right. Now, let us see how this works. Okay. The principle of operation is almost the same as an I squared L. Okay. So, if this input is low, what happens? This out transistor is going to be cut off. Okay. The current actually flows this way, okay, into the input. Okay. Basically, you have a saturated transistor at the input. Okay. This transistor is cut off, okay, and the output is going to be high. Okay. On the other hand, if the input is high, that is, at this point you have the output of a I squared L cell where the transistor is cut off. Okay. So, this input is high, that means this current will flow into the base of this transistor. Okay. This transistor goes to saturation and the output will be low. Okay. So, that is how it works. Basically, it is the same as the I squared L. Okay. All right. Now, we have to see. So, the small difference is in the here is that you have Schottky diodes at the output, okay, which is going to give you an additional drop, voltage drop. Okay. Now, whether it is going to work, that is what we have to see. Now, what is the logic swing? That is what we want to see first. Okay. Logic swing means voltage, the difference between the logic high and logic low. Okay. Now, when the input is high, say, so we have to see what is the voltage levels, okay, logic high and logic low. When the input is high, okay, say when V in is high, okay, say this we call it T1, say T1 goes to saturation, does not go to saturation, sorry, okay, because of the Schottky diode. Okay. VCE, I should rather say, I am sorry, I was talking of saturation. This is VCE is equal to, I should say, VCE min. Okay. That is, the collector emitter voltage of this transistor goes to VCE min. Okay. All right. When this transistor, when the input is high. All right. And so, what is the output voltage? V output is equal to VCE min plus the drop across this Schottky diodes, okay, VSD2, okay, and this is actually logic low, isn't it? Okay, because when this transistor is conducting, okay, the output is to be low. When this transistor is off, the output is going to be high. All right. And now, so this is the logic low. When this goes to the minimum value, you see, in a Schottky transistor, when it starts conducting, the output voltage is going to fall, but because of the Schottky diode across the base and collector, okay, it can go only up to a point, it cannot go below that, okay, which actually prevents it from going to saturation. All right. So, you know that. So, this is VL. Now, what is VH? That is logic high. Okay. Now, in this case, when this transistor is conducting, the input voltage is actually logic high, isn't it? All right, because this side the transistor is cut off. So, the voltage, okay, so the voltage whatever is the input voltage here is regarded as logic high. So, what is VH? VH is again VCE min plus VSD1, okay, that is this is VCE min plus this drop, that is the input voltage. Okay. All right. So, this is the logic high, that is at the input. Okay. So, this is actually V in. All right. So, the logic swing, okay, if I V swing is VH minus VL is equal to VSD1 minus VSD2. You see, the logic swing has been reduced even further when you compare with a normal I squared L, because of the fact that this VCE, which was going to which should normally go to 0.2 volts when the transistor goes to saturation, since this transistor does not go to saturation, this is going to be higher. Okay. Plus, you are having an additional drop because of this. Okay. So, the logic low itself is going to be much higher than in the normal I squared L, okay, and the logic high itself cannot be more than the VBE here. Okay. So, the logic swing is actually in this case, you see, it is VSD1 minus VSD2. Okay, that is the drop difference in the drops of the two Schottky diodes. Now, the drop across a Schottky diode, you know what is a Schottky diode? A Schottky diode is a junction between a metal and a semiconductor. Okay. And the interesting thing is that the cut in voltage, okay, that is when the diode conducts, okay, the voltage at which it starts conducting, that cut in voltage actually depends on the material concerned. Okay. You can adjust the cut in voltage by using different metals. Okay. So, in fact, this Schottky diode 1, okay, what people they have used in this logic. Okay. Schottky diode 1 is usually platinum silicide on silicon, okay, and Schottky diode 2 is a alloy of titanium and tungsten on silicon, okay, and this gives a difference of of the cut in voltage VSD1 and VSD2 of around 200 millivolts. Okay. VSD1 minus VSD2, that is the logic swing, okay, is around 200 millivolts, okay, 0.2 volts basically, okay, for these combinations. Okay. So, that is how this circuit works. Okay. All right. Now, so that is about the circuit. Okay. So, it is basically like an I squared L. The one advantage you can see directly here, okay, it is a Schottky transistor. So, it is a non-saturated logic, okay, and so it is going to be faster in the sense that the charge storage problems would be reduced. Okay. Now, and of course, another advantage also is from the low logic swing. Okay, you know that from the initial classes what we did, this logic swing also has an effect on the power delay product. Okay, the power delay product is directly proportional to the logic swing. Okay, that is basically because of the fact that logic swing means the difference between low and high. So, when the output voltage changes from one level to the other, from low to high, the output capacitance has to charge through only a small 0.2 volts. Okay, so, it is going to be faster. If it had to charge through a higher voltage, it would have it would take more time. So, for any high speed circuits, one has to sacrifice, okay, noise margin, okay, and the logic swing has to be reduced. Okay. So, that is also another point in favor of I mean, if you are looking at it from a high speed circuit point of view. Okay. The other advantage we shall see if you look at the circuit, the cross section of this cell, okay, how you really fabricate it. Okay. I shall draw the cross section. Okay. It is slightly more complicated when compared to the standard I squared L cell. Okay. So, what you have is again it is like a bipolar junction transistor, okay, the starting wafer. Okay, you have a p-type substrate, and as we have seen in a normal bipolar junction transistor, okay, this is the buried collector, okay, and this is N. So, that is the normal bipolar transistor, junction transistor, and this is actually silicon dioxide, and that is used for isolation. Okay. All right. So, like a bipolar transistor, you start with a p-type substrate, okay, make the buried collector, okay, all right, and then you grow the epitaxy, okay, N region, okay, where you actually make the bipolar transistor. So, this is then you make the oxide isolation, okay, then you have the base region P. So, this is the base P region, okay, all right, and you make for the P contacts, you make P plus, all right. So, here you also have a P plus, all right, this is right, this is P plus, okay, for contact, and then you have the N plus, okay, here. All right. So, this is N plus P N. Okay. Now, you have the transistor. Okay. What will now, if you look at it, okay, N P N transistor. This is the emitter, N plus P N. Okay. All right. Now, I will draw the contacts. This is one contact. All right. Then you have, I will draw two outputs. Okay. This is the emitter of the NPN, which is actually grounded. Okay. This between here and here, okay, this forms the resistance. All right. This is the resistance. Okay. This is connected to the base here. This is the input point. Okay. This is the output. I will just put O here, O1 and O2. These are the two outputs. Say this is the input. This goes to VCC. All right. Okay. So now, if you go back to the circuit, okay, VCC, this is the resistance. All right. This P region forms the resistance, okay, which is the same as the base diffusion of the NPN transistor, that is done simultaneously. Okay. So, this is the resistance which goes to the input point, okay, which forms the base of the transistor. Now, you know that in a Schottky diode, how do you make the Schottky in a Schottky transistor, how do you make it a Schottky? By, so this is the collector region. Okay. So, the base contact is, there is an overhang onto the collector region. So, basically this extension of the base contact over the collector makes it a Schottky transistor. So, this is the NPN transistor, this is the base contact, okay, and this is the Schottky transistor. All right. And this is the collector region, okay, and these are Schottky diodes. Okay. This metal onto the semiconductor, okay, this particular metal which we are putting here. So, this is one type of metal. All right. This is one type of metal which you have on the for the base contact, and there is another type of metal which you are putting for the output, okay, because this is another Schottky diode. Okay. So, this is one Schottky diode to the collector. Okay. So, you have multiple Schottky diodes connected to the collector, this is the N region. So, common N region collector for the NPN transistor, and you take the outputs through Schottky diodes. Okay. So, this is the structure of the circuit. Okay. This is a cross section view of the circuit. All right. Now, you can see another advantage if you look at this figure, okay, compared to the normal I squared L, is the fact that this particular NPN transistor is a normal NPN transistor. Okay. In I squared L, you have the emitter down structure. Okay. Here is a normal emitter up structure, okay, where the emitter is on top. Okay. And the advantage is that this is heavily doped emitter. Okay. The charge storage will be less. Okay. In the emitter down structure, the emitter area was very large, lightly doped emitter. The result, there is a lot of charge storage. Okay. This is a normal NPN transistor, which is a much faster device compared to the I squared L emitter down NPN transistor. Okay. So, these are the major advantages from the point of view of a high speed device. Number one, it is a Schottky transistor. So, charge storage problems will be less, transistor not going to saturation. Okay. The logic swing is less, with the result it is going to be faster. You know, logic swing less means it is obviously faster. And number three, because the NPN transistor is a emitter up structure, normal BJT structure, okay, you have less problems of charge storage in the emitter as you have in the normal I squared L structure, where you have a lightly doped emitter at the bottom. Emitter at the bottom means larger area, so larger charge storage. Okay. So, all these factors make it a high speed device, a high speed circuit, and power and delays of less than 1 nanosecond can be very easily achieved, okay, using this particular structure. All right. So, that is the advantage of the Schottky transistor logic. Of course, the disadvantage is you can see that compared to I squared L, okay, the technology is a bit more complicated, okay, and the simplicity is not there. Okay. You have to do, I mean, it is a more complicated technology, okay, but it is advantage in terms of speed. Okay. Well, I will just give you a reference, okay, in case you want to do any further reading, okay, on this. This is I mean just D.J. Ralston and Depay, Electronics Letters. So, this particular structure was proposed in this paper, volume 19, pages 21 to 22, January 1983. Okay. So, this is the reference for this particular logic circuit. Okay. So, that is about Schottky transistor logic, which is considered to be a high speed version of the family of I squared L circuits. Okay. So, that is about one of the ways people have tackled that problem of the propagation delay problem of I squared L. The other area where people have done a lot of work, and in fact, lot of work is also going on presently, is in the area of by using heterojunction devices. Okay. And you have what is called heterostructure I squared L. Or H I squared L. So, before going into that circuit itself, I think I should say a few words about this heterostructure. Okay, what is heterostructure, how it improves the performance, I think it is necessary. Okay. Now, as the name implies, the heterostructure is different from a homostructure. The normal devices which you have are called homojunction devices, because it is the entire device is made of the same material. Okay, maybe a silicon, or mostly it is silicon. Okay. So, all the entire device is made out of silicon. Okay. But if you have different regions of the device made out of different materials, okay, for example, if the emitter is one material and the base is a different material, you have a heterostructure. Okay. All right, these are two different materials. Now, what is the gain to be how do you gain from having a heterostructure? Okay, that is the thing which we have to see. Okay. Now, if you have a homostructure, that is the same material, the band gap, okay, of the entire structure, okay, in the entire device has to be the same, because it is the same material. Okay. Now, if you have a band, if you have a homostructure, the band will always be like this, you know. I hope it is, you know, this. If you draw the conduction band and valence band, and it is changing, okay, the conduction band has always to be parallel with the valence band. I think it is clear. Okay. That is because the band gap is the same everywhere. So, it must be parallel, okay, which means that if you have an electron in the conduction band, okay, all right, and a hole say in the valence band, the forces acting on the electron and the hole, okay, must always be equal and opposite, okay, because the forces is proportional to the slope. Okay. So, it is the electron will move this way, the hole will move this way, okay, and the forces are always equal and opposite. Okay. So, the current actually will depend on the number you have in different regions. Okay. So, but the forces are equal and opposite. But now, if you can do some what we call band gap engineering, okay, that's particular, that is can change the band gap, okay, you can modify the forces acting on the electrons and holes. Okay. So, in the same region, if you have electron and holes, you can have different forces acting on them. For example, if you have a band structure like this, Okay. And if you have an electron here, okay, and a hole here, the force on the electron is going to be this side, and the hole also it is going to be this side, all right, because of the slope, Okay. Now, which means that, okay, you can modify the forces acting on the electrons and holes. Okay. Now, you can see for yourself that suppose you have an emitter base junction, okay, and this side is the emitter and this side is the base, okay, and it is an NPN transistor. What you are basically doing by this structure is the electrons are going from the emitter to the base, okay, and the holes which constitute the base current, if you have a band like this, you are preventing it from going from the base to the emitter. Okay. There is a force acting on the holes which is in a direction opposite. No, it is a force which is preventing the holes going from the base to the emitter. Normal structure, it would have gone from base to emitter. Okay. So, what are you doing basically? You are going to increase the beta of the transistor, isn't it, because the collector current, okay, which is basically due to electrons moving from emitter to base, that is going to get increased, whereas the holes, the base current is going to get reduced, because the force acting on the holes is preventing it from going to the emitter. Okay. So, that is what that is in a sense, okay, what you do in a heterojunction bipolar transistor. You have a wide band gap emitter, okay, material, the emitter material is made of a wider band gap material and the base of a narrower band gap material. Okay. So, if you have a structure like this, okay, you can increase the gain of the bipolar transistor, okay, by having a wider band gap emitter. So, I shall again go into slightly more quantitative analysis. Okay. You know that if we take a emitter base junction, again NPN transistor, say an emitter base junction, okay, this side is emitter, this side is base, okay, and if I plot the charges, so on the emitter side, so this is the contact, say you have the excess charges, I am just plotting the excess charges. So, this is the, say, the collector, okay. So, the charges may be like this, okay. So, these are minority carrier stored charges on the emitter and the base, all right. Now, if we neglect the recombination in the base, okay, we can make write an approximate relation for the beta of the transistor. Okay. So, this is, say, the emitter width, okay, from here to here, and this is the base width WB. WE is the emitter width and WB is the base width. Okay. Now, what is the collector current approximately? Say I am writing the collector current, I will write, okay, IC is equal to A, that is the area, Q dN, that is the diffusion coefficient, and the slope of the electron distribution, okay, in the base, all right. So, that is the diffusion current, all right. Okay, this is well known, we have already seen that. So, what is dN dx? That is what is of interest to us. Okay. dN dx is the slope of this base profile. Okay. So, the slope is nothing but the height of this triangle by the base. Okay. So, the height of the triangle is going to be given by AQ dN. So, the height of the triangle is Ni squared, Ni, I write B here because it is in the base region, that is all right, Ni squared by the doping in the base. So, this is the, what is Ni squared by Nb is the minority carrier concentration at thermal equilibrium, okay, into exponential VBE by VT. Okay, that is the value at the depletion region edge, no, on the emitter base junction depletion edge. Okay. So, this is the height of the triangle, okay, and the base divided by WB, which is the base of the triangle. So, that is dN dx. Okay. All right. Similarly, if I want to write IB, okay, and I assume that the base current is primarily due to the injection of holes from the base to the emitter, okay, this slope will give us the base current. Okay. And so, by similar analysis, okay, IB will be equal to AQ, instead of dN you have dP because it is holes, diffusion coefficient of holes, Ni E squared by Ne, that is the emitter. Okay. Ne is the doping concentration in the emitter, We is the emitter width, again exponential VBE by VT. All right. Okay. Here of course, I neglect that the base recombination in the base, okay, which is going to be true especially if you have very short base widths, okay, which is in fact true in the case, mostly in the case of heterojunction bipolar transistors. Okay. Now, so what you have now is beta is IC by IB, okay, IC by IB. So, you have dN by dP, okay, then you have Ni B squared, Ni E squared, Ne by Nb, We by Wb. Okay. So, this is normally the same, it is almost the same relation as for a homojunction, except for the fact that we have written it in terms of Ni squared and Ni E squared. Okay. The why we have written it is normally in a homojunction the Ni is what? Ni is the intrinsic carrier concentration, okay. In the emitter and the base would be the same, but in a heterojunction, okay, they are going to be different, okay, because of the difference in band gap. Okay. Now, you know that Ni squared, that is the intrinsic carrier concentration, depends very much on the band gap. If you have a larger band gap material, the intrinsic carrier concentration is less. Okay. That is already we have seen that in the first few classes, we have discussed that. Okay. So, and in fact, Ni squared is proportional to exponential minus Eg by kT. Okay. Ni is proportional to minus exponential minus Eg by twice kT. So, Ni squared is proportional to exponential minus Eg by kT. So, what you have is Ni squared B by Nie squared, okay. This is going to be equal to what? Exponential Eg of the emitter minus Eg of the base by kT. Okay. All right. And this is sometimes referred to as delta Eg, that is delta Eg is the difference of the band gap of the emitter material and the base material, okay, exponential delta Eg by kT. All right. So, you see that if you look back into this expression now, okay, I just write it again, beta is equal to I just rewrite it again, dN by dP, Ne by Nb, WE by WB exponential delta EG by KT. Okay? All right. Now, what is this value of delta Eg? If you take a normal system, you know, HPT system with the most commonly used heterojunction materials which is in use is aluminum gallium arsenide on gallium arsenide. Okay, traditionally has been used as the heterojunction HBT material. Of course, there are not a lot of other materials which have been used later. Okay. So, if you take aluminum gallium arsenide, that is aluminum 0.3 gallium 0.7 arsenic, this is a material, okay, on gallium arsenide. So, gallium arsenide, you see for each gallium atom you have one arsenic atom, okay, that is a compound. Now, what you do is AlGas is 30% of the gallium atoms have been replaced by aluminum in gallium arsenide. Okay. So, for each arsenic atom or you can say for every 10 arsenic atoms you have 7 gallium atoms and 3 aluminum atoms. Okay. So, it is written like this: aluminum 0.3, gallium 0.7, arsenic. So, it is a compound, okay. It is a ternary compound, okay, 3 materials, okay. And this material AlGas, for this the band gap difference delta Eg is 0.374 electron volts. Okay. Now, if you take exponential delta Eg by KT, okay, for delta Eg as 0.374, okay, at room temperature this is almost, the value is almost 10 to the power 6. Because a KT is just 26 millivolts. Okay. All right. So, this is an enormous number, 10 to the power 6. All right. So, you see that by just changing the material, the heterojunction material, the emitter material, okay, and having a wider band gap material, okay, and having a variation in band gap, okay, you can have a very large increase in beta. Okay. So, in fact, I mean you cannot really have such high betas, because once you have in this relation, if you know this what is going to happen is then the beta will be determined not by this. Basically what we have been talking of is emitter efficiency. Okay. If this ratio becomes so large, okay, beta will be determined by the other factor, that is the base transport factor, that is the recombination in the base. Okay. All right. Basically it is all right. So, the beta is no longer going to be determined by this. Okay. And so, it is no longer advantageous to have such a high value, you know, of this factor. So, what you can do is, now suppose, okay, in a homojunction, in a homojunction we have Ne by Nb, that is the doping concentration of the emitter to the base is made very large. Okay. The emitter to the base doping concentration in a homojunction is made very large. Okay. That is necessary to achieve high betas. We have already discussed that. Now, for a homojunction transistor, say Ne by Nb is 10 to the power 2, that is 100. Okay. And you have a corresponding heterojunction transistor, say where Ne by Nb is equal to 10 to the power minus 2. That is, the base doping concentration is more than the emitter doping concentration by a factor of 100. Even then, because in a heterojunction you have an extra factor of 10 to the power 6, okay, the beta if you just consider it to be determined by emitter efficiency, is still going to be 100 times more than the corresponding homojunction, is not it? So, in a heterojunction bipolar transistor, okay, because of the large gain which is achieved because due to the difference in band gap, okay, usually the base doping concentration is made much larger than the emitter doping concentration. Okay, that is quite normal in a heterojunction bipolar transistor. It has got its lot of advantages. I need not go into all that because it take a lot of time. Okay, some of the advantages you can think for yourself. The base resistance is reduced, which has got a lot of which is very important in high speed transistors. Because you have a higher doping concentration in the base, you can go for shorter base widths and you do not have to worry about base punch through and other effects, okay, which you would normally have to worry, if you have a shorter base width. So, you can actually have very short base widths if you have high doping concentration in the base, because if the doping concentration is high, the depletion widths is going to be less and you do not have base punch through. So, there are a lot of other advantages. Okay. So, in a normal heterojunction bipolar transistor, you have a wider band gap emitter and a lightly doped emitter, all right, and in a and the base doping concentration is much higher. Okay. Now, so you can very well imagine that in an I squared L, where the problem was that you have a lightly doped emitter, okay, and you had a lot of charge storage there, okay, it is no longer a problem because of the fact that you now have a wider band gap emitter material. Okay. And you know that basically the charge storage is proportional to Ni squared by N, is not it? That is Ni squared by N when N is the doping concentration in that region. Okay. The problem was that N was less, the charge storage is proportional to Ni squared by N when N is the doping concentration in any region. Okay. The problem was because the doping concentration is less, the minority carrier concentration would be more. But here Ni squared itself is going to be very much less because of the wider band gap material. Okay. So, the charge storage problem, okay, is not of so much concern anymore, because that is normally what is accepted in a heterojunction bipolar transistor. You have a lightly doped emitter. Okay. Also, you have a heavily doped base region, so which also reduces the doping the minority stored charge in the base. Okay. So, that is the advantage of an heterojunction bipolar transistor. Okay. Basically, the structure is like this. Okay. You have a heavily doped base and you have a lightly doped wider band gap emitter. Okay. So, this heterojunction, okay, has been used in I squared L to improve the speed performance of I squared L circuits. Okay. In fact, a lot of recent work on I squared L which has come out has been in this area of heterostructure I squared L. Okay. And you can see that why you should have a better performance if you use heterojunction. I think it is clear now. Okay. So, the heterostructure I squared L, okay, has a structure which is quite similar to the which is a Schottky transistor logic circuit, which we had already seen. Okay. And it consists of resistance and this is the BJT, okay, and you have the Schottky diodes here. Okay. In fact, this is not a Schottky transistor, okay, this is a normal transistor. Okay. That is the only difference between a Schottky transistor logic circuit and this heterojunction I squared L circuit. Okay. So, normal transistor, you have Schottky diodes here, okay, and So, this is how it is going to work, all right, and we shall in the I think in the next class, okay, we shall take up the circuit, or I think if I have some time I can just continue. So, this is V in, this is VCC, this is R. Okay. Now, okay. So, for saturation, okay, we have to ensure that this, so basically this is not this is a saturated logic, okay, and you can imagine that if this transistor goes to saturation, there is no problem. Okay. This is 0.2. Okay. Now, we have to ensure that this transistor actually goes to saturation. So, what is, so for saturation, okay, beta times IB must be greater than IC. This is the well known relation. Okay. All right. Now, what is IB? IB is equal to VCC minus VBE by R. Okay. And what is IC? So, you have, this is going to individual bases, all right. So, you have VCC minus VCE plus VSD by R, okay, into the number of, I should say, fan out, okay, the number of collectors. So, each of them is going to conduct, okay, all right. When this transistor goes to saturation, this is connected to the base, all right, as input to the next stage, say, all right. So, current will flow this way for the next stage. So, what is the current which is flowing? VCC minus this voltage here, which is VCE plus VSD divided by R. So, the number of fan outs, okay, here in this case you have 3. So, you have 3 times that current. So, that is the total current which is going to flow. Now, if you put it here, so beta must be greater than IC by IB. Okay. You have to ensure that the beta of the transistor is greater than VCC minus VCE plus VSD by VCC minus VBE into fan out. Okay. So, once this is ensured, okay, the transistor actually goes to saturation. Okay. All right. And well, what are the different voltages? Okay. Usually, you know, this is in heterojunctions, as I said, you have aluminum gallium arsenide and gallium arsenide. The band gap of gallium arsenide is 1.42 electron volts compared to 1.1 for silicon. Okay. Aluminum gallium arsenide is much larger. Okay. It's almost 1.8 electron volts. Okay. So, the voltages, okay, these voltages VCE, VBE and even VSD, that is the Schottky diode on gallium arsenide, the cut-in voltages of any junction, okay, it depends on the band gap of the materials. Okay. So, these are going to be much larger compared to that of silicon. Okay. So, in fact, we shall continue with this discussion, okay, in the next class, all right, and we shall look at the structure, okay, and see some of the results, okay, on these heterostructure I squared L. In fact, there has been also very recent results, okay, some people are doing a lot of work in this, and maybe this is the area where I squared L is really going to make a mark, okay, in future.